My name is Thijs Roumen, Hasso-Plattner Institute. Our software tool KerfCanceler allows modifying cutting plans so that they not only work when fabricated on the laser cutter they were designed for, but also on other machines that remove much more or much less material. Today, laser cut models are shared in the form of 2D cutting plans. As the result of sharing, however, users may fabricate on machines that remove more or less material, which is also known as kerf. The embedded mechanisms therefore come out too wide or too narrow, which causes them to slack. In this paper, we make mechanisms work reliably by compensating the amount of material removed by laser cutting them. This bearing operates reliably, the slider does not wiggle, and the gear that performs the height adjustment engages perfectly with its counterpart, all independent of the amount of material removed by the cutter. We achieve this by something we call kerf-canceling mechanisms. Mechanisms that continue to perform their functionality independent of the amount of material removed by the fabrication machine. We built a software tool KerfCanceler that allows users to modify cutting plans with these kerf-canceling mechanisms. Let me explain how kerf-canceling mechanisms work at the example of the bearing. This bearing holds an axle in place, even when we increase the amount of kerf. The inset closes the gap caused by kerf exactly, and all users need to do is to jam the inset in place, so there's no need for tuning. The mechanism we added to this bearing thus cancels out the kerf produced by the laser cutter. Let's see how it does that. So the kerf-canceling bearing consists of two design elements, the jammer and the inverse scaler. The shape of the jammer is derived from a Nautilus spiral. We place an inset of the same shape inside the cutout. On a machine that removes more material, the inset comes out too small and would just fall out of the plate. However, the self-similarity allows me to lock the inset in place by rotating the inset. So the shape of the jammer holds the inset in place. In turn, the inverse scaler holds the axle in place. This works because the shape of the inverse scaler is a flipped version of the jammer. More kerf results in more rotation. The inverse Nautilus shape narrows down the cutout by exactly the same amount, resulting in bearings that reliably cancel out any kerf, as shown here with increasing amounts of simulated kerf. In the microscope we started out with, there was not just a bearing, but also a sliding mechanism and a gear to control the height adjustment. For these we also have kerf-canceling equivalents. The kerf-canceling equivalents of these leverage simple wedges to linearly reduce the increased size of the cutouts. And these mechanisms combined allow me to make this microscope completely independent of the amount of material that is removed. So in conclusion, the mechanisms I just showed you cancel out kerf. In combination with spring fit, which makes joints kerf tolerant, this allows me to fabricate this microscope on any laser cutter. I see this as a step towards my bigger goal of portability. Having laser cut models function reliably, independent of the specific laser cutter material or material thickness that was used. Portability in the context of computer science made source code valuable, as the resulting code could be shared and used by others. It was a prerequisite for more advanced collaborations, such as remixing and modifying code written by others. I think that by achieving this in the context of laser cutting, we could, just like in computer science, stand on the shoulders of giants and truly increase the complexity of what we as a community are able to produce. Thank you for your attention.